To us, it appears that time doesn't stop or slow down for anyone in this universe. It's always running forward without waiting for anyone or anything. But is time really like this? Special relativity theory tells us that time is really not like this. Time is not the same for all across the whole universe. Different observers feel different times at different places. So why is this? How is this possible? Let's see. Einstein's special relativity theory starts with two basic ideas. The first postulates that the laws of physics are the same in all frames of reference. Imagine your friend is standing at the platform of a train station and you are in a train traveling at a constant velocity. Constant velocity means an object is moving in a fixed speed and fixed direction. This motion doesn't have any acceleration, deceleration, and does not change direction. So your friend is on the platform. From his perspective, he is at rest and you are heading forward. But from your perspective, who is traveling at a constant speed, does not feel any motion. And so you also can claim to be at rest. The rest of the world can appear to be running towards you. If the train windows are closed, there is no outside reference point. Thus, you believe you are at rest. As all the laws of physics will apply to both your friend and you, both of you can be considered to be at rest. To explain more simply, let's take a look at a mosquito in a flying plane. Now that the mosquito is sitting on the back seat, it wants to fly to the pilot room. If the laws of physics is not the same for a moving plane, it must travel above the flight speed. But there's nothing like that, and the mosquito feels at rest on a moving plane. So the normal effort is enough to reach the pilot's room. Now let's come back to the train scenario. You are in a moving train and your friend is on the platform. Whatever your friend is doing on the platform, you can also do in the moving train. However, the speed is not the same for all observers. Let's say the train is moving at a constant speed of 100 kilometers per hour, and you throw a football at the speed of 20 kilometers per hour. From your perspective, the ball is traveling 20 kilometers per hour because you are at rest inside the train. But from your friend's perspective, who is on the platform watching the train, he feels the ball is traveling at a whopping 120 kilometers per hour. Let's say you have another friend who is running on the track towards your train at 10 kilometers per hour. Now, if you measured the ball speed, he would judge it to be 130 kilometers per hour. How can the same moving object be showing different speeds? Because speed is relative, it can vary from one to another. Different observers can measure different speeds on the same moving object. Special relativity's other postulate is that the speed of light is the same for all observers. The speed of light is constant and it always shows the same value for all frames of reference. Let's take a simple example. You and your friend are standing opposite each other. He has a flashlight and your friend flashes the light. If you could measure the speed of light quick enough, you would measure it at around 300,000 kilometers per second. No surprises yet, as you're both at rest. But now you're running towards your friend at the phenomenal speed of 10,000 kilometers per second, and he flashes the light. You would measure it still showing the same value of 300,000 kilometers per second instead of showing 310,000 kilometers per second. This is due to the fact that the speed of light is constant. It's the same for all the observers, no matter where that observer is at rest or in motion. In order to maintain the constant nature of the speed of light, space and time experience weird features. So what is time? Even today, we still don't know exactly what time is, but we do have some basic understanding. We've all agreed that all the clocks in our world tick at the same rate. We've all agreed on how long some things take to happen and what things happen at the same moment. These basic things of time we experience in our everyday life. But the constant nature of light says that it's all wrong. How? Imagine there are two nations, Nation A and Nation B, and they want to sign an agreement. The problem is that they both want to sign the agreement at the same moment, and they found the procedure too. The procedure is that the leader of both nations need to sit at the opposite sides of the table, with a light bulb fixed over the middle of the table. Turn on the light bulb, and when the light reaches both leaders' eyes, they can both sign simultaneously, because they already know that light always travels at the same speed. Both nations' leaders decide to sit exactly the same distance from the bulb. So the event begins, they turn on the light, and the light reaches both leaders at the same moment. The agreement is signed simultaneously by leaders, and everyone is happy with the result. A few months later, they decided to sign another agreement, but this time, both leaders want to do it differently. Even though they have many different options, both leaders have an extreme love of trains. So they set up the same scenario in a moving train. The train goes on. The light flashes and goes to each leader, reaching them simultaneously. They sign, and again, everybody in the train is happy with the result. But the people standing on the platform started fighting because the people from Nation B complained that Nation A leaders signed the agreement first. How did they come up with that conclusion? Now take a look at that event again. The train is moving, the light flashes. Leader A is coming towards the flash. Leader B is moving away from the flash. So they saw that the flash first reached leader A because he was moving towards the flash. They already know that light always travels at constant speed. Leader B was moving away from the flash, so it took a longer time to reach leader B compared with leader A. From the perspective of those watching the event from the platform, both leaders didn't sign at the same moment. But from the leader's perspective, who were in the moving train at constant velocity, claim that they signed at the same moment. We already know that when an object travels at a constant speed from the perspective or frame of reference, it can claim it is at rest. Now let's move on from the platform perspective. Let's make a simple to understand event. We'll draw a line when the flash takes place, and draw a line when the flash reaches leader A versus leader B. So from this line, we can clearly see that the flash reaching leader B needs to travel a longer distance compared to leader A. Light always travels at the same speed. If it has to travel further, it takes a longer time. So who is right here? The leaders inside the train or the people watching from outside? The reality is that both are right. So what is it telling us? The constant nature of speed of light means that the events take place at the same time, even though from the perspective of one group of people, the events don't take place at the same time as from the perspective of other groups. One group of people don't realize any time difference, and the other group of people witness a time difference on the same event. It is not an optical illusion, it is reality. The thing that happened from one person's perspective does not happen at the same moment as from the other person's perspective if they are in relative motion. Now we move on to the next step. Let's take a clock. Even though we have many different types of clocks to explain time dilation, we will take a light clock to understand this more easily. The beauty of the light clock is that its mechanism is simple. However, it's not different from any other clock we have. In a light clock, there are two mirrors, with a light ball bouncing between them. Let's consider the light ball as light. Every time the light ball goes up and down, or tick-tocks, it counts as 1 second. Now we take another light clock. We'll keep one clock in stationary, and we will put another clock into motion. So with the clock in motion, we can clearly see the light ball is moving at a diagonal path. Also, we can see the counts on both clocks are different. Why? Look at the trajectory on the moving clock. It's double diagonal. The amount of one full up and down movement takes longer compared to a stationary clock. This is because light needs to travel a longer distance, but the speed of light is constant, and its speed always is the same for all observers. So in the moving clock, each tick-tock happens at a slower rate. Slower tick-tocks mean time runs slowly. In the moving clock, 1 second takes longer than the stationary clock. Time runs slowly on the moving clock only for the outside observer who is watching this event. But for whoever is inside the clock, they don't feel any time difference because they also travel along with the light clock, so they are unable to feel the light ball take the diagonal path. So they don't feel time slowing down. As we already know, when an object moves at constant velocity, it can claim to be at rest. So when an object is in motion, its time slows down. But why don't we see time dilation in our everyday lives? Let's take a look at the time dilation formula. Let's take two clocks, one on Earth and another on a rocket in space. Let's make the rocket move at 10% of the speed of light. At this speed, we can't really see the time difference. There is a time difference, but it is still hard to notice. Now increase the velocity of the rocket to 70% of the speed of light, and we can really see the time difference. The elapsed time on the rocket ship is less than from the perspective of those of us here on Earth. Now let's move the rocket 98% of the speed of light, and now we can really experience the extreme difference between two clocks. So from our view who are on the Earth, the clock in motion time is ticking off very, very slowly. To understand more deeply, we will take another example. The light clock is placed on the moving train. Now, our train velocity is at 10% of the speed of light. At this velocity, there is some time difference, but not much. It looks like it is almost following the exact path of the light ball, going straight up and down. Then we increase the velocity to 70% of the speed of light. At this point, we can clearly see the diagonal path of the light ball. Now, if we move the train extremely near the speed of light at 99.99%, there is a really big difference in the diagonal path. So here, the light ball doesn't make a single tick while the stationary clock continues at its normal rate and completes a lot of tick-tocks. Therefore, time dilation is a universal phenomenon. However, its effects become significantly noticeable only when moving near the speed of light. At everyday speeds, time dilation does occur, but its impact is extraordinarily small. We have seen so far everything is theoretical and formula-based, thus we can't actually conclude time dilation is happening when an object is in motion. So are there any experimental things that have been proven by real life? There are many experiments proving that time dilation really exists. Let's take two simple experiments. The first example is the most straightforward experiment that verified time slows down for the moving clock. In 1971, scientists Hefele and Keating took two synchronized atomic clocks. One was left stationary, and another one was placed on a plane. The plane flew all around the world a few times. When the plane landed, they compared the two clocks. They found that a different amount of time had elapsed on each clock. The difference was 60 nanoseconds in fact. The time difference between them is exactly what Einstein had predicted. So this experiment established very directly that time on moving clocks ticks at a very different rate from stationary ones. Another experiment was conducted with the lifetime of a muon. Muons are particles similar to electrons, but with a lifetime of only 2.2 into 10 to the power of -6 seconds. After that, it breaks apart. So after 2.2 into 10 to the power of -6 seconds, its lifetime ends. Scientists found that sometimes muons take a little extra time to disintegrate. That's when muon particles are in motion, and they take longer to break apart. However, muons themselves always take the same time to disintegrate, but our perception as people who are watching this event experience as muon particles take a longer time to disintegrate. But muon particles still claiming that they disintegrated exactly after 2.2 into 10 to the power of minus 6 seconds. However, this observation proved that time really slows down when an object is in motion. So feel this, you and your friend are at the same age, and both of you don't know about special relativity theory. You left your friend on Earth and you are traveling in a rocket near the speed of light after traveling and return back to the Earth and meet your friend. Now you say that only 6 months passed for me, but your friend replies, but 40 years have already passed here on Earth. This is how time dilation works. This is the beauty of special relativity theory. It is a wonder how Einstein figured out this feature with the constant nature of speed of light. He is absolutely a genius.